Hello and welcome to section which introduces the first data processing module of the course using DJI Terra software. By the end of this session, you will have generated your 3D point cloud, which is geo-referenced to the WGS84 global coordinate system. It will also provide step-by-step instructions on how to generate a 2D ortho photo using the raw images captured by the L1 sensor. In the first part of this module, we will briefly introduce DJI Terra software and discuss the different processing options available. This first section looks at installing DJI Terra onto your PC. It will briefly introduce the different Terra packages available. There are 4 main packages available when you purchase DJI Terra. These are Cluster, Pro, Agriculture and Electricity. For surveying and mapping applications, we recommend purchasing DJI Terra Pro. This version incorporates an optimized point cloud accuracy function, which is useful when processing datasets demanding a high survey grade accuracy. For the duration of this module, we will be using DJI Terra Pro to process our L1 dataset. For L1 data processing, you need to ensure your computer is equipped with the NVIDIA graphics card and has at least 4 GB of VRAM. The CPU must incorporate at the very least an Intel i5 core processor and have sufficient storage. For every 1 GB of raw point cloud data, your PC will require 4 GB of memory. To activate the DJI Terra online license, we first need to download the latest version of DJI Terra from the DJI website. The list providing all of the Terra versions can be found under the Download Center link. Ensure you download the latest version of DJI Terra to your PC. You now need to enter your DJI account details into DJI Terra. This should be automatically prompted as you load up the app. Once you have logged into your DJI account, you should be able to see the DJI Terra display. Next, we need to activate our Terra Pro license onto the PC. Go to the profile icon at the top right of the screen and click on Activated Licenses, Activate New License. It will automatically send us to a web browser where we are required to input our new activation code that is provided as a 6-month free trial in the L1 box alongside our DJI account name. Once successfully activated, you should be able to see the ID, expiry time and binding status of the activated license. Click Device Binding and then press Bind to bind the license to the current computer used. Once completed, it should say Bound next to the license of the corresponding ID under Activated Licenses. DJI Terra was developed as an easy-to-use mapping software that will help you map, visualize and capture your drone data. It has applications in a variety of industries including construction, agriculture and energy. Once you have activated your DJI Terra license, you are ready to start the processing. Along the left pane in the mission library, you can either specify the flight path mission planning or select the relevant processing model. You can either do a 2D map, 2D multispectral map, 3D reconstruction or Lidar point cloud processing. You will primarily be using Lidar point cloud processing for your raw L1 data. However, you will first be using the 2D map function to process the photos captured by the 20 megapixel camera. It looks at the raw L1 data that is stored on the micro SD card of the L1. When the SD card is put in your computer, all the folders can be transferred to a raw data folder on your PC. For the purposes of this course, we have named our folder Zenmuse L1 Raw Data. On closer inspection of the file stored in this folder, all of the photogrammetry and LiDAR data is stored in a single folder on the microSD card. Each of the individual photos in this file have a known corrected GNSS position at the photo center of each image and are saved as a JPEG file so processing can begin automatically. As for the remaining files in the folder, there is a mix of information. In this folder you have stored a CLC, CLI, CMI, IMU, LiDAR, RTB, RTK, RTL and RTS file. You can only process your L1 LiDAR data from an RTK network if each of these files are present in the folder. Here is a breakdown of what each file contains. The CLC file contains LiDAR camera calibration data. The CLI file contains LiDAR IMU calibration data. CMI contains visual calibration data. The IMU file contains the inertial navigation data. The LiDAR file contains the LiDAR point cloud raw data. There is also an MNF file, which is visual data, which is currently omitted from the raw data with no impact. The RTB file contains RTK base station data. The RTK file contains the main antenna data for the RTK, whereas the RTL file contains the rod arm data. Finally, there is an RTS file which contains RTK sub-antenna data. If you want to check the results of the calibration files, it can be opened up in a separate Notepad document. However, the results from the other folders cannot be read in the Notepad, and the results can only be assessed once in DJI Terra. In DJI Terra, go to New Mission and then select 2D Map under where it says Reconstruction Mission. We are aiming to process a 2D orthophoto. We are going to call our project Zenmuse L1 2D Map. Under Add folder, we can add the folder that contains the raw JPEG images and positional data from the drone. The locations of the photos should load up into the display. As for the mapping scene, this is going to be set to urban, as our scene contains some buildings towards the centre of the project area. The resolution can be left on high as this produces the highest quality orthophoto. The computation method can be left on standalone computation. For the output coordinate system, select WGS84 as a known coordinate system. Once the settings have been set, we can start the reconstruction. Before starting the reconstruction, DJI Terra will process the photos first. When the reconstruction is finished, it should produce a 2D orthophoto of the survey area. An orthomosaic is an aerial image of an area corrected for perspective, camera tilt, lens distortion and topographic relief. The corrected image has no distortion whatsoever and the scale is uniform across the orthophoto. This makes it possible to derive true distances as they would appear on the surface. As you zoom into the orthomosaic, you can clearly see how visible the checkpoints are with the 20 megapixel camera captured at a 60 meter flying height. Alongside the 2D orthophoto, you are also provided with a quality report that provides information on aspects such as RTK status and the camera calibration information. Also included in the 2D quality report is a preview of the DSM and report of the scene overlap. To assess the accuracy of the survey, you can refer to the ground sample distance, which represents the ground according to 1 pixel. This can be found under the map information overview. Ideally, you are looking to achieve a GSD as close to 1 cm as possible, or lower. The GSD for this surveying project shows that it was 0.016 meters. The lower your GSD value is, the more accurate your survey will be. To further assess the accuracy of the orthomosaic, prior to processing, you would need to go to GCP Management generate an aero triangulation report, as this compares the checkpoint data to the coordinates embedded in the image. We will now go over the recommended parameters for processing your Lidar dataset in DJI Terra. We first need to go to Lidar Point Cloud Processing and click New Mission. We're going to call this project Zenmuse L1 Lidar Processing. However, for your data, I would recommend naming the mission after the name of the survey site you covered. Once you have created the project, the first course of action is to load the raw data into DJI Terra. We need to locate the folder where the L1 data is stored and then click Select Folder. The point cloud could be processed from this point here, however there are some further parameters that are worth changing first. If your survey has covered a particularly large site, you can also merge all your flights into one directory to generate one large LAS file, rather than having multiple smaller point clouds. Firstly, ensure that the scenarios have been set to point cloud processing. Under this comes point cloud density. Point cloud density refers to the number of coordinates collected per unit area. As you can see, Terra provides 3 levels of density: high, medium and low. High point cloud density refers to 100% of the data being included for point cloud processing, whereas medium is 25% and low is 6.25%. A low reconstruction would generate an LAS file much quicker than a high reconstruction. If your computer is short on storage, it may fail to generate a high density point cloud, whereas it may succeed on the low. For the parameters, we have 2 options. The point cloud effective distance will be left at the default 250 meters. This refers to the cloud points with a distance greater than the set value from the Lidar emission center, which will be filtered out during the post-processing. Setting this value too low will remove most points from the dataset. Secondly, the Optimize Point Cloud Accuracy tool can be used to optimize the adjustment of the point cloud data scanned at different times, which improves the overall accuracy of the dataset. For surveying and mapping applications, it is recommended to enable the Optimize Point Cloud Accuracy tool. However, for power line reconstruction, we would recommend disabling this. It is worth noting that processing time will be longer when this function is enabled. In the output coordinate system, you can specify the coordinate system for your project. We want our dataset to be loaded into a known coordinate system, as arbitrary coordinate systems locate the point data in blank object space. It provides a choice of either a geodetic or a projected coordinate system. Geodetic coordinate systems represent where the data is located on the Earth's surface, whereas projected coordinate systems represent how to draw the 3D surface onto a flat 2D plane. You can leave the altitude settings on default. The reconstruction output can be selected to the format you require. If you require multiple file types, you can select one-on-one. The format used for display of 3D point clouds in DJI Terra is PNTS and is selected by default. LAS is the industry standard binary format for laser scan data and airborne Lidar outputs. Encoded within this file is the XYZ data, as well as other elements such as the intensity of the return pulse and the RGB value. As for the formats that aren't selected by default, there are the PLY, PCD and S3MB file types. If you wish to load your process data into third-party software, it is worth checking what file types are fit for import. Usually most softwares accept LAS files. We can now start the processing and select Start Reconstruction. If the processing is draining too much memory from your computer, the reconstruction can be paused and resumed at a later time. Looks at the result files generated from DJI Terra. Once the data has been processed, the file will be named with a number and not the project's title. This can be found in the same drive as your DJI Terra application. It should be under DJI Terra Data. The first output is the LAS file. This industry standard format is in the version v1.2 and records information such as RGB colour, reflectivity and the echo that each 3D point belongs to. The second file is the SPET file, also known as the post-process trajectory file for the mission. This file contains trajectory information for the process solution. As per the LAS file, this can also be exported to third-party softwares and does not require a second adjustment if the Optimize Point Cloud Accuracy function was enabled. Encoded within this binary format is information regarding a GPS time, geodetic coordinates, altitude, XYZ velocity, XYZ acceleration, XYZ angular rate, as well as roll, pitch and platform heading. The SMR msg.out file is the post-process precision file containing a root mean square error for the drone's position, velocity, as well as roll, pitch and yaw in each of the XYZ directions. Once the reconstruction is finished, the point cloud automatically shows in the display. It can be viewed by either RGB, reflectivity, height or return. RGB colour shows the point cloud in its true colour form, and enabling this feature before flight allows the drone to collect the photogrammetry data also. Reflectivity shows how the light emitted by the scanner interacts with the Earth's surface. There are two main ways the light interacts with the surface. Diffuse reflectors are surfaces that are rough in texture, reflecting the emitted pulse in a variety of directions. There are also spectral reflectors that return the pulse at a defined angle. Land types with greater surface roughness, such as an asphalt road, will have a high reflectivity at 90%. Smooth spectral reflectant surfaces such as lakes have a reflectivity closer to the 10% mark. However, this value can also be affected by the scan angle, range, moisture content and surface composition. With all these factors in mind, LiDAR does not always lead to consistent results when viewed in terms of reflectivity, but this does not take it away from the fact that this view has important applications in feature detection, land cover classification and identification of wetland areas. The point cloud can also be viewed by height. This shows how the elevation changes across the site, highlighting the high and low points of the dataset. Finally, the point cloud can also be viewed by return, which displays a number of backscattered rays recorded by the L1 sensor. On our screen now we have two returns as dual echo mode was selected for our flight mission. However, if triple echo mode was selected, this would provide a green band also, highlighting the points that provided 3 returns. As we can see, the areas highlighting dual return are mainly located around the sides of the buildings and in the areas of vegetation. This is what we would expect, as the beam of light is split up as it hits the surface, hence why we get 2 returns. There are also some basic zoom and navigation tools to use in DJI Terra. Firstly, you can zoom in and out of your point cloud using the tools shown on screen now. As for the view tools, the point cloud automatically displays as a 2D overhead view. If we want to return to 2D view, we can click the button that says 2D. Terra also provides a 3D point of view which can be selected by clicking the button below. In practice though, you will mainly use the mouse for navigating around your point cloud. The final view allows you to roam between 2D and 3D views and zoom right into the dataset. Navigation in this view will be explained more in the next session. There are a variety of tools included in DJI Terra that can be used to pan and take measurements from the point cloud. Firstly, we will introduce the pan tools included with DJI Terra. Using the left click of the mouse, we can pan around the point cloud and zoom into areas of interest from a top-down nadir view. If we want to zoom into the data from an angle that isn't perpendicular to the surface, we can use the left click of the mouse and the control button to change the perspective. If we zoom close to the buildings at the centre of the dataset, it is almost like a virtual reality view, as we are viewing the data at the time of capture from the ground. If we click and hold the mouse, we can move around the dataset. We can zoom into particular features of interest and then rotate the view in the point cloud. For those involved in forensics or accident investigation, this is a useful tool as the data can be quickly captured on the site and then processed and viewed back in the office. Once you have returned to a standard overhead view, we will start to look at some of the measurement tools in DJI Terra. Under where it says annotation and measurement, there are 4 main tools for collecting measurements in DJI Terra. Firstly, the coordinate tool can be used to verify the precise location of a point relative to WGS84 and present it in terms of latitude, longitude and altitude. For those who are not using Terra Solid in the next module, this could be used to check the accuracy of the control, providing that coordinate transformation has been computed for either the Terra measurements or the control points. Secondly, the distance tool can be used to measure the distance between 2 points. We are going to use a building at the centre of the dataset as an example. One left click places the marker down and the second click places the second marker to derive the distance. To save the measurement, right click the mouse and press save. All saved measurements are stored on the right side of the screen. If you are wanting to measure each face of the building, 4 separate measurements could be taken, or if you wanted to calculate the total perimeter, the line tool could be drawn around the entire building before saving the measurement. The distance is saved as a horizontal distance measurement and a straight distance measurement. Once we are happy with the measurements, we can export the data as an Excel spreadsheet by going to Manage All and then Export. If you go into your DJI Terra directory, you should save this into a new folder. We are going to call this folder Measurements and store the Excel file in here. This allows all the DJI Terra outputs to be stored into a single directory and just keeps things more organised. If you open up the recently saved Excel file, you can see the information is provided in terms of horizontal distance, straight distance and vertical distance. We will now look at the area tool for calculating the total area of a given object or place. This works in the same way as the distance tool, using both left clicks and right clicks. Once we have our area, we will get results for both the projection area and the fitted area. The projection area refers to the 2D measurement of a 3D object by projecting the shape to an arbitrary plane, whereas a fitted area refers to the actual measurement relative to the WGS84 coordinate system. The projection area refers to the 2D measurement of a 3D object by projecting the shape to an arbitrary plane, whereas a fitted area refers to the actual measurement relative to the WGS84 coordinate system. The output can be exported to the same folder as the distance measurements. Finally, DJI Terra provides a volume tool and is especially useful for stockpile measurements and deriving the cut and fill volumes. Once the points have been selected around the area of interest, the volume is presented in terms of cut and fill. This is calculated relative to either a base plane from the lowest point or a base plane relative to the mean elevation of the points. Cut volumes refer to the land that is above the base plane, whereas the fill volumes refer to the land that is below the base plane. For earthwork applications, a cut volume would inform engineers that land needs to be excavated, whereas a fill volume would tell engineers that land needs to be filled or raised. The processing output also produces a quality report that provides a breakdown of the processing time for each component. Firstly, the input information overview shows us the time spent loading the pose data and point cloud data into DJI Terra. Also listed are the various file formats and the resolution of the processed point cloud. Finally, the performance review outlines the processing time for each component. The largest amount of time was allocated to the LPP time, which refers to the amount of time spent optimizing the accuracy of the point cloud reconstruction. As you can see, this takes up a large proportion of the total processing time. This final section will look at the potential sources of error you may come across when processing your point cloud and provide solutions to the problem. Firstly, you may get an error message that says reconstruction failed. If you receive an error message saying that the reconstruction has failed, this could be to do with the amount of storage available on your PC. Usually, if there are many active projects open in your DJI Terra directory, it will take up a lot of the allocated space, and future Lidar projects cannot be processed. Usually, if you can successfully manage to process low density point clouds, but not high density datasets, this will indicate you have a storage problem. If you navigate to the DJI Terra directory and locate the folders where all your projects are saved, they should be listed by numbers increasing from 1. If you delete all the folders you no longer require, this will send them to the recycle bin. So ensure these folders are permanently deleted from the recycle bin to allow the Lidar reconstruction to complete successfully. Error message: the Lidar point cloud positional data is abnormal. If you receive this error message, it will most likely be because the RTK connection was disconnected during flight, or there was no RTK base station data available. Alternatively, this could occur if you have an RTK connection, but the drone remains stationary and is stuck in static hovering positioning mode during the data collection. If you receive this message, you should try the PPK workflow. If this fails, you will need to recollect your data. Error message: the raw data is missing or the file path is wrong. This error will indicate that the RTK base station data is missing or the RTK network turned off during flight. Alternatively, if the file suffix is wrong or the RTK files are saved in the wrong format, this could cause this error message. If you receive this error message, you should try downloading third-party GNSS data from the Ordnance Survey website and use the PPK workflow. If this still fails, you will need to recollect your data. Error message: the raw data of the Lidar point cloud is abnormal. The collection time of the Lidar file does not correspond to the collection time of other files. This is most likely caused from the files being copied incorrectly. Ensure that the correct files are in the correct directory and the collection times align. If you use the PPK workflow, ensure the times covered from the base station data match the times you completed your survey. If this fails, you will have to recollect your data. Error message: Lidar point cloud accuracy optimization failed. For this error, the easiest solution is to disable the optimized point cloud accuracy function. However, if your solution demands the high accuracy output, we would recommend recollecting your data. In the flight parameter settings, it might be that the altitude is too high, the speed of the drone is too fast, or there are insufficient overlap points in the dataset. Error message: Lidar point cloud positional calculation failed. This indicates that the contents of some files are incorrect or missing in the directory. It could also highlight that the time values in the IMU and RTK files do not overlap. The best solution for this error message is to recollect the data. If you use the PPK workflow, ensure that the existing RTB file has been removed from the directory and replaced with the OBS file. If you use the PPK workflow, ensure that the existing RTB file has been removed from the directory and replaced with the correct OBS file. Error message: quality of the point cloud model is poor, or the results have severe data loss. Receiving this notification could point towards a variety of things. Firstly, if the survey mission had begun before the IMU had completely warmed up, this could introduce a weak accuracy into the results. Secondly, a poor positional accuracy indicates an error with the RTK. This could be down to the N-trip connection providing a float solution rather than a fixed one, or it could be that the DRTK2 was accidentally moved during the survey as it was recollecting the RINEX data. The best solution for this error message is to recollect your data. If you used the PPK workflow and downloaded your base station data from a third-party source, ensure that the GNSS baseline is 10 km or less and you have not accidentally selected a base station that is far away from your survey area.